Hi, in this video we will cover another techniques of solving the second order ordinary differential equations, which is for the second order differential equations with undetermined coefficients. In the previous videos we have covered preliminary theory on linear equations, reduction of orders, and then we have covered homogeneous linear equations with constant coefficients. So for now we will be covering the undetermined coefficients. Okay, to solve a non-homogeneous linear differential equations which is in a general form of y double prime plus pxy prime plus qx and y equal to gx, because it is a non-homogeneous, we must do two things. We must do two steps. The first is that we have to find the complementary function which is related to the homogeneous part, okay, the left hand side of the equations, which we learned previously. For homogeneous equations, the complementary function will be giving us a c1y1 plus c2y2. This is denoted as yc. And then the second parts that we need to solve is the particular solution, which is related to the non-homogeneous equations. We will walk you through on how are we going to utilize the superposition approach to solve the undetermined coefficients. Okay, so basically for us to complete, or for us to solve the non-homogeneous equations with undetermined coefficients, we need to have two parts of the solution, which is yc, which is the complementary solution or complementary function, and also the other one is that on the particular solution. Okay, therefore the general form of the equation is that y equal to c1y1 plus c2y2, which is the complementary solution, and we have yp, which is the particular solution. Okay, but for this kind of method, which is the superposition approach, we can't really use it for all type of undetermined coefficient. We cannot really use it for any kind of coefficient which is related to the non-homogeneous part of the differential equations. We can only use this superposition approach for these four types of gx. Gx is the non-homogeneous part of the equations. We can only use it for if gx is equal to a constant, okay, only if gx is equal to polynomial functions, and also gx could be an exponential function, and also can only be used for gx if gx is sine or cosine function. So other than these four, we cannot use the superposition approach. We have to utilize other techniques for us to solve the equations. Okay, so some example on the functions that are appropriate for superposition approach. For example, if gx is equal to constant, something like this, gx equal to 10, which is gx is constant, gx is equal to sine 3x minus 5x cosine 2x, which is the combination of sine and cosine function. We have polynomial function of the order of 2. We have this combination of polynomial and also exponential, and the combination of exponential and sine and cosine function, and also polynomial function. So it can be in combination of those four functions that we have outlined earlier. It can be dedicated or combinations. Some examples that we can use superposition approach to solve the second order ODE is that something like natural log, the reciprocal functions, tangent, okay, the inverse sine, sine is okay, but inverse we cannot use superposition approach. Okay, let us look into the example to illustrate the solving or solution techniques for the undetermined coefficients by using the superposition approach. Okay, let us look into the first example where we have this y double prime plus 4y prime minus 2y equal to 2x square minus 3x plus 6. So we notice that our gx is equal to a polynomial function here. So first thing first is that we have to solve on the homogeneous equation for us to find the complementary function. So we notice that we have this y double prime plus 4y prime minus 2y equal to 0, which is a linear equation. So linear equation, we can solve it by using the techniques that we have previously learned and we have previously discussed. So for this case we have if you notice that all of the coefficient or all of the coefficient for the homogeneous equation, they are all constants, so we can use homogeneous with constant coefficient. Okay, to solve that we can find the auxiliary equations, which is m squared plus 4m minus 2 equal to 0. We found out that the auxiliary equation are giving us a real and distinct root. Okay, a real and distinct root which are equal to -2 minus square root of 6, -2 plus square root of 6. Okay, therefore our complementary function is c1y1 plus c2y2, where y1 is equal to negative natural exponential of -2 minus square root of 6x, and y2 is natural exponential of -2 plus square root of 6x. So you can refer to the previous techniques for the solution on the complementary function. Okay, next is the step 2. Okay, step 2 is to find the particular solution. For us to find the particular solution, we have to look into what is our gx. So if our gx is a polynomial function, for this case it is the order of 2. Because it is a polynomial function, we provide an assumption that our particular solution will be in the form of polynomial function as well. So we just assume for now that our yp is equal to ax squared plus bx plus c, because we want to match the non-homogeneous part of the equation. So we have our gx is equal to 2x squared minus 3x plus 6. Now we just assume for now the solution for gx or particular function or particular solution is also a quadratic polynomial. Okay, so we need to find the specific coefficient of a, b, and c, which is in the particular solution. Okay, so how do we do that? Is basically we need to differentiate yp so that it will be matched into the equation that we have here. Okay, meaning that we have to, because we have the derivatives of y double prime and y prime, we need to differentiate it once and twice so that we can include yp into the second order differential equations. Okay, so what do we do next is we differentiate yp twice. First is yp prime equal to 2ax plus b, and then yp double prime equal to 2a. So the first derivative is 2ax plus b, second derivative is 2a. So now we substitute yp, yp prime, and yp double prime to the differential equations. Okay, when we substitute it, the next thing is just algebra. You need to do comparison between the left hand side and right hand side. Okay, whatever that is on the left hand side must be equal to the right hand side. And then from there, when we rearrange the equation, we have this for x square, negative 2a is equal to 2, 8a minus 2b equal to negative 3, and 2a plus 4b minus c equal to 6. I believe up until this point, this is quite simple. You can actually solve the equations. Okay. So from there we can observe the form of the last equation, which is similar on the left hand side and the right hand side. So we can do comparison. When we do comparison, so this is what we have discussed earlier. Negative 2a equal to 2, 8a minus 2b equal to negative 3, and 2a plus 4b minus 2c equal to 6. Then we just solve the equation. Okay, when we solve the equation, this is supposed to be okay, for this case, this is supposed to be, if I'm not mistaken, that one is 2. This is supposed to be 2. Okay, negative 2a is equal to 2, so a is equal to negative 1. And then 8a minus 2b equal to negative 3, b equal to negative 5 over 2, and then c equal to negative 9. Okay, therefore our yp is equal to negative x square minus 5 over 2x minus 9. So basically the general solution is given as yc plus yp. So this is yc complementary function plus yp, and then so now our y is equal to c1 natural exponential negative 2 minus square root of 6x plus c2 natural exponential of negative 2 plus square root of 6x minus x square minus 5 over 2x minus 9. So it is quite simple actually. The solution is quite straightforward and quite simple. You just need to solve the homogeneous part, and then after that you find the particular solutions. Okay, let us look into another example, which in this case our gx here, okay, our gx is basically a sine function. Okay, so it's basically a sine function. So how do we estimate or how do we assume the solution for the yp for this case? Okay, first is that we notice that our function is a sine or cosine function. Then what we do is that for a sine and cosine function, we assume that yp to be a combination between sine and cosine, because we know that when we basically perform a derivative or differentiation, cosine and cosine will change intermittently between sine and cosine itself. Okay, so yp now, because of we have a sine or cosine function, we have yp equal to a cosine 3x plus b sine 3x, because our the sign here is actually sine 3x. So next is that we do similarly we do differentiation twice, because this is a second order of ODE. When we do differentiation twice, the next step similar with the previous example. What do? Is that we substitute this yp, p prime and yp double prime into the equation of y double prime minus y prime plus y. Then we compare with the 2 sine 3x. Okay, so basically this is what we have, and then when we rearrange the equation, we have negative 9a minus 3b plus a cosine 3x plus negative 9b plus 3a plus b sine 3x. We can simplify that further, which is negative a minus 3b, that because we have no cosine here, this will be equal to 0. Negative 8b plus 3a will be equal to 2. Okay, so we solve it further. Okay, this is what we have. This is what have been outlined earlier. Negative 8a minus 3b will be equal to 0. and then negative 8b plus 3a will be equal to 2. So then we can solve for a and b. So a will be 6 over 73, b will be negative 16 over 73. So the particular solution now will become 6 over 73 cosine 3x minus 16 over 73 sine 3x. You can solve for the complementary functions on your own. Okay, another example is that we have this gx, okay, where our gx is equal to the combination between a polynomial function and also an exponential function. Okay, how do we go about this? The first thing first is that you can find the solution for the homogeneous part, which is related to the complementary functions. You can see that this is equal to m squared minus 2m minus 3 equal to 0. And then this is case 1, real and distinct roots. Okay, so basically we will have m equal to negative 1 and 3. So our for case 1, our solution is that yc is equal to c1 natural exponential of negative x plus c2 natural exponential of 3x. Okay, for step 2, we solve for the particular solution or particular functions, which is in combination of polynomial, which is polynomial of first order, 4x minus 5, and also the exponential function, which is natural 6x natural exponential of 2x. So our gx is basically a polynomial plus exponential. Okay, polynomial and exponential. So how do we go about this? So basically what do we do is that we have to break our gx into g1 and g2, so polynomial and exponential function. Then we assume that our particular solution to be also two parts. One is the polynomial and the other one should be the exponential. So for the polynomial, we assume that because the polynomial is at the degree of 1, so we assume that yp1 is equal to ax plus b, which is also the first order polynomial. And then because of we have the exponential function, which is the combination between a polynomial as well. Okay, 6x multiplied by natural exponential of 2x. Therefore we have two components for the polynomial part, which are the cx natural exponential of 2x plus the natural exponential of 2x. Okay, thus to find that's our yp, okay, or the particular solution now is the combination between linear and exponential part. Okay, so we differentiate it twice as previously. Okay, when we differentiate, this is the first differentiation, and then second differentiation, second derivatives. First derivative is a plus c plus 2d natural exponential of 2x plus 2cx natural exponential of 2x, and then second derivative is equal to 4c plus d natural exponential of 2x plus 4cx natural exponential of 2x. Okay, next I think you know what to do. You just substitute into y double prime minus 2y prime minus 3y, and then we compare it with 4x minus 5 plus 6x natural exponential of 2x. So further to that, we found out that the final solution is that a equal to negative 4 over 3, b equal to 23 over 9, c equal to negative 2, and d equal to negative 4 over 3. So by now you can actually estimate on what kind of assumption that we need to put up based on the gx. Okay, so we just substitute all of the value into the yp, then we have the general solution in terms of yc plus yp. Okay, so these are some example on the form of yp, the assumption that we have to make based on the gx that is being given in the equation. So you can refer to the list in the handout. Okay, you can always refer to the list in the handout much later. Okay, the next simple exercise that you can do is that based on the previous table, okay, try to determine the particular solution, okay, the form of particular solution for the following A, B, C, and D. So you can try this exercise on your own, and the solution is basically available on the slides, on the handout of the slides. You can refer to that solution. I hope by now you can basically understand. You can basically try the solution on your own. Okay, so I think that's it for the solution based on superposition approach for the undetermined coefficients for second order ordinary differential equations. Thank you for your attention.